An important part of audit is to be able to determine a sample size. Using sampling will help us to reduce the amount of work involved in performing an audit, and yet could still provide us with enough information to be able to provide assurance to management on whether or not our controls are working correctly. For example, when we're going to do sampling, we can use this as an important tool when we cannot examine the entire population of a subject area. Say, for example, we have everybody in a hockey arena, and we want to know how many fans in that arena are then fans of the opposing team. It could be very difficult to go and count everybody in the arena and try to determine the actual number then of fans for the opposing team. So what we would often do is take a sample of a certain number of people and from that be able to extrapolate whether or not the sample size represents then the actual total population. So therefore the sample itself is a subset of the data that is actually available and will be audited overall. We take then the sample to infer the characteristics of the entire population based on that sample that we have chosen. But an important part of this is trying to determine the reliability of that sample. Is that sample actually truly representative then of the entire population? In many cases, using a sample will help us to measure the adequacy of a control. Say, for example, a financial transaction. We want to make sure that all transactions over a certain dollar limit have been approved. We then can check by taking a sample of all the transactions over that dollar limit to make sure they have proper approval. If we find that many of them don't, that would mean that that control is actually then not adequate. There are a number of different types of sampling methods that we could use in trying to determine that subset of samples we'll use. These are based on mathematical formulas based really on the mathematical laws of probability. We want to calculate a suitable sample size, a sample size which is large enough to be truly representative, but not so large that means we've done a lot of unnecessary work that could have actually proven the point much earlier in the process. We use therefore something called the confidence level to know how much confidence do we have in whether or not our sample is truly representative of the entire population. We will collect the sample items from the entire population and from those then evaluate the results. We can do non-statistical sampling, and non-statistical sampling is based then on auditor judgment, where the auditor will then take a number of samples without any type of mathematical rules and just try to see which ones then would fit then the criteria that is going to be measured. This is much more of a subjective measurement. For example, if we have transactions that range in value from $0 to $100 and we are looking specifically for fraud, we may look at those types of transactions that are right at the edge of $100 or that are very small that maybe could have been unnoticed. The auditor, instead of taking a truly representative sample from all of the transactions, would then use their subjective judgment to say it's more likely that we'll find a fraud case within those outlying areas rather than from sampled across the entire population. So what we do then is when we take that type of non-statistical sample, we'll select more samples from those areas that we consider to be potentially of higher risk. However, this brings in a risk to the audit itself, and that is that the sample we have chosen may not be a true representative of the entire population. For example, going back to the hockey arena type of scenario, if we took then 10 people coming in the door and said how many of those are then fans of the opposing team, that may not be representative of the entire population within the arena. It could be that we had a whole group of people come in together that were fans of the opposing team, and we could easily think that maybe 40% of the fans were actually then for the opposing team, when that was not actually truly representative. On the other hand, if I said, I took a sample from the first 3 or 4 rows of the people attending the hockey game. It's most likely that the people in those more expensive seats are going to be the fans of the home team, whereas the fans of opposing teams are usually going to be higher up within the stands. And if my population I chose was from that first few rows, that also could give me a biased or incorrect result. That means the auditor, having drawn an incorrect sample, will also then come to the wrong conclusions about whether or not that sample is correct and indicative of the entire population. This is something we would call a sampling risk, which would then also mean that the audit itself, which was based on that sample, is going to be then incorrect. So what is the countermeasure for this? The countermeasure for sampling risk then is to use statistical sampling to quantify the probability of the error. And this is something we'll call then the confidence coefficient. So there are a couple different methods of sampling. Attribute sampling, which is a compliance test, tests the presence or absence of a certain attribute. We gave the example before that I could look at transactions over $5,000 and make sure that every one of those had then a second level of approval. What I would do is take a sample of those and from that see whether or not the approval was actually given. That is, I'm looking for a specific attribute. And that could indicate that maybe 1 out of those 10 was not properly approved. I could maybe then extrapolate that to say that 10% of all those transactions of the entire population has not had the proper approval or the proper attribute. That would produce then a percentage or a number of the number of items that are not compliant with that rule or control. Variable sampling is often used when I'm going to do substantive testing. This is, I identify variations from the norm. For example, in variable sampling, if we see that the average transaction that goes through a process is, say, $50, then quite often I will look for those types of transactions that are outliers, those that are not within the normal area. Those that are above 75 are those transactions that are below 25. If I have a very widely dispersed population, I will often look for these types of variables to be able to see whether or not there are then problems within those areas that are probably of a higher risk. So attribute sampling, which is also known as fixed sample size or frequency estimating, estimates, as we mentioned a moment ago, the rate of occurrence of an event. For example, missing approvals on a financial transaction or, say, on a change request form. However, if I'm looking at an area where there's a lower chance of then, should we say, a missing attribute, I may instead use something like stop and go sampling. Stop and go sampling would be where I went through then, say, 10 transactions. I checked those transactions, and if I found that every single one of those was okay, I could make then the assumption that, well, the number of errors is actually quite low. At that point, I might say I'm going to stop the sample because obviously the compliance with the controls or the attribute is actually being met in all 10 cases that I checked. However, let's say, for example, in those 10 cases I checked, I found one that was not properly approved. Then I might continue and increase the sample size so I find out, is it truly 10% or is it maybe 1 out of 20 or 1 out of 30? So in other words, depending on the results and auditor judgment, I'll either stop the sample collection or I'll continue it on in order to get more precise or accurate information. Another type of sampling which is used especially when we're looking for fraud is discovery sampling. This is where the rate of occurrence of, say, a problem is extremely low, and I'm looking for a specific type of event. And instead of creating a sample size of, say, 10 out of 1,000 transactions, I will look specifically for a certain type of transaction, a transaction with consecutive, should we say, invoice numbers, or I'll look for a transaction just below the threshold for approvals, which is more likely where we would find a fraud or discover a fraud, as its name indicates. With variable sampling, also known as dollar estimation or mean estimation sampling, I'll then estimate the monetary value or another weighting factor from the sample. For example, I may take a 1,000 transactions, and from those 1,000 transactions, I will then determine what is the mean or what is the average value of those transactions. And say, for example, the average then was $50. Then I could take a sample size, a sample of maybe 20 of those 1,000 transactions. I'll calculate the mean for those 20. Is that also approximately $50? If it turns out that the mean or the average from the sample is quite different from the mean or average of the entire population, it means my sample is not really accurate enough. And what I'm trying to do is determine, in many cases with variables, I'm trying to determine those areas that are, shall we say, outliers, are more likely to be a risky scenario. When I do quantitative sampling methods, often based on statistical methods, say for example I want to look at a stratified mean per unit. I want to make sure that of a population of everybody in the hockey arena, I then would understand that in a hockey arena, I have people from very young ages to very old. And if I want to do a true sample size, I want to make sure that I choose a certain number from each population group, those under 20, those between 21 and 40, those between 41 and 60, and those between, say, 61 or older. And in that type of a case, I would make sure I've chosen a couple of samples from each of those sub-areas, or those, I've subdivided the population into those groups. That means I should have a much more accurate reflection of the entire population. Another way, of course, is unstratified mean. And that it would be where I just take the first 20 people to walk in the door, and I use those as my sample size, even if all of those 20 just stepped off a bus together and they're from a local high school and they're all the same age. We, of course, have to then determine what is the difference estimation. This is what is the difference between the actual values of my sample and the values of then the entire population. There are a number of definitions we use when we talk about sampling. For example, we talked about the confidence coefficient a moment ago. The confidence coefficient represents what is the confidence level or the reliability factor of my actual sample. It is a percentage estimation of whether or not the sample that I've used is truly representative of the entire population. If I want to have a level of confidence that my sample is 95% likely to be truly representative of the entire population, that's considered to be a fairly high level of confidence. If I'm going to have such a high level of confidence, it usually means I'm going to have to have chosen a larger sized sample. The level of risk then is calculated as the difference between a perfect sample, which would be sampling 100% of the items, and the confidence coefficient. So if I have a confidence coefficient of 95%, we would say that our level of risk is 5%. And we see this quite often when we see pollsters indicate then which electoral party someone is going to vote for. They'll say that the results are plus or minus 3%. That is their level of risk, 19 times out of 20, which would, of course, indicate for us a 90% then confidence factor. Precision is the acceptable range difference then between the sample and the entire population, also expressed as a percentage. If I want higher precision, or have a population with higher precision, that means I could use a smaller sample size. For example, if I'm going to sample the opinion of everybody at a high school, Everybody at a high school is within a very narrow, shall we say, age band. All of the students are really between, say, the ages of 14 and 18. And so our level of precision is actually fairly high. Whereas if I'm going to look at the precision of everyone attending a hockey or a baseball game, then my population spread and age spread is much wider. And that would mean that to be precise, I would need a larger sample size. Now, if my precision of my group is too low, that means I could end up with a sample size that is unnecessarily large in order to have a higher level of confidence. So we determine what is our expected error rate. That is, a percentage of the errors that could exist. If I have, of course, a higher error rate within my sample, that could mean, of course, that we require a larger sample size. The sample mean, and here we get into a slight problem. The mean is often considered to be the midpoint of all of the items within a population, and yet many people confuse the term mean to be the same as the average. Say, for example, you have 3 children, a 3-year-old, a 4-year-old, and an 8-year-old. If we take the average would be 3 plus 4 plus 8 divided by 3, which is, well, 15 divided by 3, so the average age of those 3 children is 5 years old. Well, nobody is 5 years old. We have a 3-year-old, a 4-year-old, and an 8-year-old. The other way of calculating is to use the mean, and the mean would be the midpoint, the child that is then between the other two, which is the 4-year-old. The problem is that there's a lot of dispute about whether or not we should use the term mean or use the term average. In this case, don't worry about it too much. The whole point is that it really is the way to determine what is the average or middle of the entire population. And that is important often when we're determining the deviation then from the norm. We take, for example, the average person has an IQ of, say, 110. But we have some people with very low IQs and some people with very high IQs. The idea, though, is that most people, if we follow a simple bell curve, are within a fairly narrow band then of a similar level of intelligence quotient. However, there are outliers. There are people that are further away from that, either a higher or lower. That would be the deviation from the norm. And quite often in calculating then our sample size, we want to make sure that the sample mean is really the same as the population mean. If I've determined a sample size which has an should we say, representation of people with a higher IQ, then that is probably not representative of the entire population. In other words, if I took a sample of a number of students at a university, we would expect then that the IQ of those students would be higher than the normal population overall within a town, for example. We also have to understand how many errors would be tolerable. Well, how many times could I be wrong? And the tolerable error rate is really the maximum number of errors that could be tolerated before the number of errors becomes material. This, of course, is used a percentage in calculating then our precision values. We have, of course, looked at a sample, and yet we find that a few of the items within our sample really did not fit the rule. And therefore, we have what we call, say, an outlier, or we have something which is an exception. How many exceptions would we allow and still have confidence that our sample was still an accurate and a reliable sample? We then, of course, look at the distribution of variables. We used this before when we talked about the population standard deviation. Within a hockey arena, the deviation of ages is very wide. We have a fairly flat bell curve with many people, of course, at both the lower and higher ends of the scale. Whereas within a high school, we have a very narrow list of actual ages, and very few people are going to be below or above then the average age of the student. So to do a sample, We select a sample based on what do we want to prove. What do we want to prove in the way of then confidence coefficient? What do we want to then ensure that our sample size would truly be accurate? So how many items do we need to choose? What will be the population overall, and what is the population then of the sample size? We'll look at whether or not we want to do statistical or non-statistical sampling, variable, stop and go, or attribute sampling, and from that calculate what would be the appropriate sample size, select the actual sample items, and then evaluate those sample items to be able to find what are the results that we can glean from that sample, that we can use then as a substance within our audit report. In summary, we should point out that as a CISA, we do not have to be a statistician, nor do we have to become an expert in sampling, but we should be familiar with these terms and the processes used in creating and selecting a sample that could be used for audit purposes.